introduction. I will speak about extensions of the Gross-Zagier theorem, but before that, I thought I'd start by giving some introduction to the general picture relating algebraic cycles to L-functions and explain how this fits into the big picture. Okay, so what we're interested in is relations between algebraic cycles and L-functions. And I'd like to start by considering two examples. The first is analytic class number formula, which all of you have undoubtedly seen, which says the following: that if you start with, if you have K a number field, then the zeta function of K has a simple pole at s equals 1. And if you take the residue at s equals 1 of zeta ks, this has some expression involving various invariants attached to the field K. So it looks like this: 2 to the R1, 2 pi to the R2, the class number regulator, and then you have the roots of unity, the square root of discriminant. Okay. All right. So that's something all of us have seen. Here's another example. This is the conjectural Boltzmann-Dyer formula, conjectural ST, which says that if you start with an elliptic curve, say over Q also, then firstly the Mordell-Weil group is finitely generated. That we know. What it says is that the rank of the Mordell-Weil group is the order of vanishing at s equals 1 of the L function LES. But secondly, it also says that if you look at the leading term, so let's call this R, then the leading term there's some formula for the leading term that has this form. You divide by some period, and then here you get various invariants attached to E, the Tate-Shafer-Witch group, the regulator, there's a Tamagawa factor, and then you have the E-tor, the torsion squared. Okay, and these formulae are remarkably similar, right? If you think about it, the 2 pi corresponds to the period out here. The class number corresponds to the Tate-Shafer-Witch group. There's a regulator here which involves, this is a determinant, and what you have inside there is logs of units. And here, likewise, you have a regulator, and this is also a determinant. And what you put in there is the neuron Tate. You take a basis for EQ mod torsion, and then take the matrix whose entries are pi, pj, where you use the neuron Tate pairing, and then take the determinant of this thing. Okay, so I want to remind you about what we know about this conjecture, since it's only a conjecture. These sides, this is often called the algebraic rank, and this is called the analytic rank. And what we do know, so what do we know about BST? So what we do know is that if the analytic rank is 0 or 1, so if Rn, then in fact the algebraic rank equals the analytic rank, and SHA is finite. So the Tate-Shafer-Witch group is some kind of local global obstruction. It's not known to be finite in general, but in this case it is. So I guess there's work of Coates-Wiles and Rubin in the CN case. And in the general case, this falls from Gross-Zagier and Kolyvagin. And recently, there's been a converse to this as well, which is due to Skinner and Wei-Shang by two different methods. And the converse says roughly that if the algebraic rank is 0 or 1, And if you know finiteness of SHA, then this implies the analytic rank equals the algebraic rank. And this condition can be weakened somewhat to some condition of the Selmer group, but it's not very important for us. OK, so what I want to emphasize is some facts about the structure of this proof. OK, so what is the structure of the proof? So the first step, so step 1, is modularity. Your elliptic curve is associated to a modular form f of weight 2 on gamma naught of n, where n is the conductor of the elliptic curve. Okay? The second step is a kind of geometric form of modularity. Modularity tells you that the L-adic representation associated to E also occurs in x naught of n, in the h1 of x naught of n. And then by faultings, one knows that there's a map from x naught of n to E. So a surjective map from x naught of n to E. Okay. The third step, and this is what Gross and Zagier do, is you pick an imaginary quadratic field, suitable imaginary quadratic field. Okay. And what Gross and Zagier do is they pick this such that this is split at all primes dividing n. Now, this condition that k be split at all primes dividing n has two consequences. So the first of these consequences is that if you look at the L function of E, not over Q but over K, then E over Ks in fact vanishes to odd order. And the second consequence is that you can actually, because k is split at all the primes dividing n, you can make this construction, so-called Tigner point construction. Okay. So very quickly, where this comes from is because k is split at all the primes dividing n, you can write n as n bar in OK as a product of ideals. And then if you look at the isogeny C mod OK to C mod n inverse, this is a cyclic isogeny of degree n, and so it gives you a point on the modular curve x naught of n, which by the theory of complex multiplication is defined over the Hilbert class field, h of k. Okay. Now you can use this map to map it down to E, go to EH, and then you can take a trace and you land in EK. All right. So on the one hand, you force the L function to vanish to odd order. On the other hand, you can explicitly construct a point, right? And so you can ask, is this point non-torsion? And the famous Gross-Zagier theorem, what is the following? What they show is, so let's call this point something. Let's call this point P. What Gross and Zagier prove is that the Néron-Tate height of P, so they prove an explicit formula. This is exactly equal to the derivative up to some constants that don't matter so much. This is the the derivative at 1. So if you knew somehow, if you picked this field somehow such that the derivative is non-vanishing, then you'd know that the point is non-torsion. And in fact, there's some analytic input that goes in where if you start with an elliptic curve of rank 0 or 1 over Q, you can pick your case such that the elliptic curve over K has rank exactly 1. And then once you know that, then you know that this point is non-torsion. OK, so this tells you, this gives you a sort of lower bound in the rank, but then you need Kolyvagin. So Kolyvagin, in fact, proves in this case that if the analytic rank L over Ks has order 1, then he proves that SHA is finite, and in fact the rank the rank of Ek is 1. And the extra ingredient that one needs is it's not enough to use the single Tigner point. One also has to use Tigner points over ring class fields. And these you can construct devices of degree 0 using this, and then use the Abel-Jacobi map or the p-adic Abel-Jacobi map. These give you certain cohomology classes, and then Kolyvagin applies a so-called derivative construction to get Kolyvagin cohomology classes. And it's this entire system of cohomology classes where you use all these different ring class fields that's important to prove that SHA is finite and that the rank is, in fact, 1. Okay. And this work of Skinner and Wei Zhang also builds in all of these ideas and uses many others. But the point I want to emphasize is somehow the Tigner point construction is really important. Without that, you have nothing. Okay? You don't even have finiteness of SHA in this case. In the CM case, you can when you something about finiteness of SHA, but because of elliptic units in that case. All right. So here's a sort of little motivational picture that I'll draw and maybe set aside here. OK, so this is just for fun. Okay, so here's a picture that I like to keep in mind. As number theorists, we're interested in motives over number fields. So I'll use the word motive very loosely. For me, this will just mean either you can think of a piece of the cohomology of some variety, or you can think of this as a compatible system of realizations. Okay, and so in the two examples that I wrote down, the motives I'm thinking about here are either z of 1 over k, or h1e with a Tate twist of 1. Okay. Now, if you start with a motive, you can associate it on the one hand arithmetic invariance, and on the other hand analytic invariance. So the two examples I'm thinking about here are the zeta function zeta ks at s equals 1, or LE at s equals 1. Okay. And the arithmetic invariants I'm thinking about are the class group here and the Tate-Shafarevich group here. Now, you might notice I left out something that you might consider important, in fact, very important. I'm going to put that in the middle. And those are, in the first case, the units, and in the second case, the Mordell-Weil group. Okay. So what you'd like to do is to sort of understand how the arithmetic and the analytic sides are related to each other. Okay. But you need this middle circle. It's very important. This is what interpolates between the arithmetic and the analytic side. Okay. So this goes by many fancy names. Some people, it's called motivic cohomology, or I think of these in terms of Chow groups or higher Chow groups. But the point I wanted to emphasize is that, for example, in the second case, even to understand finiteness of SHA, you really needed to explicitly construct elements in the middle. Okay? So the key sort of problem that I want to talk about is the following. How does one explicitly construct? So elements in this middle circle. Okay, the key word is explicit, right? How does one make this explicit? Okay, so the way this works is so you could be at the center or you might not be at the center. For example, here the functional equation is s to 1 minus s, so you're not at the center. To 2 minus s, so you are at the center. And the way this works is if you're at the center, this should correspond to some element in the Chow group, and if you're away from the center, it's a higher Chow group. And in today's talk, I'm going to focus entirely on the center. So I'm only going to talk about what happens at the center. So let me tell you what the general conjecture is at the center. and it's going to generalize the Burt-Swinnerton-Dyer. Okay. So the conjecture at the center is the following. I'll just state this for varieties. So let's say this is due to Bloch and Beilinson. And so what it says is the following. Suppose X is a smooth projective variety over K. K is going to be a number field. Let chow Jx 0, and I'll say in a second really what this is. The group of homologically trivial cycles of codimension J on X. Okay. So what this is defined in the following way. I'll write this as ZJX0 by ZJX rad. Okay, so let me just say what this is. ZJX is just going to be the free abelian group on subvarieties of codimension J. Okay, that's what it is. This admits a cycle class map, and ZJX0 is the kernel of the cycle class map. And then you have to go mod the cycles that are rationally equivalent to 0. So the example to keep in mind is, of course, if X is an elliptic curve and J equals 1, then chow 1 of E0 is in fact exactly equal to the model weight group EK. Okay, so the conjecture is going to say something about this group. The first part of this conjecture is that chow Jx0 is a finitely generated abelian group. Okay, so this is the analog of the model weight group being finitely generated. The second part of the conjecture will predict exactly what the rank is in terms of an L function. So the rank of this group is supposed to be the order of vanishing at S equals J of the L function associated with the motive H2J minus. Okay. So again, if X is an elliptic curve and J is 1, this is the L function of H1, and at the point S equals 1. That's exactly what you get from BSD. And there's a third part of this conjecture which will predict what the leading term is in the Taylor expansion. And I don't want to write, I'm not going to write this out explicitly. It's something like what you see in Burt-Swinnerton-Dyer, except let me say a word about the regulator. So in BSD, there's a regulator, and the regulator involves height pairings, right? So here also, this is going to involve height pairings. This involves a regulator, which is a determinant of height for height pairing. But now one has to be careful because the height pairing is a kind of arithmetic intersection. So if you're not in the middle arithmetic degree, then this is going to be an arithmetic intersection between cycles of complementary arithmetic degree. So the height pairing will be from C at J cross C at J prime, where J plus J prime equals dimension of X plus 1. Okay? All right, so this will come up later in the talk, which is why sort of emphasizing this, that somehow if you're away from the middle, then you really need cycles in sort of different codimensions. This height pairing makes sense. Okay. So the problem with this conjecture is that we don't know anything even about part A of this conjecture, or very little. So the case of divisors is easy, but once you go to codimension 2 and higher, we really don't know anything about the finite generation in any non-trivial case. Okay, so that's a huge problem. So we don't know that the guy on the left-hand side is finitely generated. On the other side, we don't know that these L functions admit analytic continuation. So that's another problem. Right. So how do you? So this problem seems totally unapproachable. So what do you do? As in all of mathematics, when you don't know what to do, you change the question. So we're going to ask a different question. So sort of a new question. No, you know this for projective space, for example, right? And you know it for divisors, but we don't even know these for fake projective spaces. So these are like fake projective planes, so something that looks like whose homology looks like P2 but is not P2. We don't know it for those guys as well. No, not a single non-trivial example. Yeah. The problem is that the only way we know how to study this is via the Abel-Jacobi map. And the Abel-Jacobi part of this conjecture, which I didn't write down, is that Abel-Jacobi should be injective mod torsion, and we don't know that. So it's sort of, you go in circles because you don't know, you can only study it via the Abel-Jacobi map. And you know nothing about the kernel of the Abel-Jacobi map. The problem is that over C, the kernel of Abel-Jacobi can be really large. So there are sort of non-torsion things in the kernel. Well, you don't expect that over Q bar. So you really need to somehow differentiate between C and Q bar when you do this. OK. So we're going to sort of change the question. So the new question you might ask is the following. Let's not just start with any variety, but let's start with an L function that is of interest to us. Okay? Start with an L function for which you know analytic continuation, perhaps because this came from modular forms in some way, from automorphic forms in some way. Okay? So the new question is the following. So start with some motive M. Such that we know analytic continuation of LMS. Okay. And suppose that, in fact, LMS vanished at the center. At the center, and suppose the center was some integer j. Okay. Then sort of vague question you can ask is, can I realize M? So can we find a variety X, right, over a number field such that M is contained in H2j minus 1 X? And if you did that, so bear with me for a second, if you did this, then you should expect, because of the vanishing of the L function, that in fact there's a non-trivial element, a non-torsion element in chow j x0. Okay? And then can you produce a non-torsion element in chow j x0? And of course, it's not sort of a random thing. You want it to correspond to this motive in some way. So I'll just put an M out there. And if you think about it, this is the question that Gross and Zagier really answer. What they do is they set themselves up such that the L function has sign minus 1. And so it vanishes. And then they look for the point, and they find this point. Okay? But we can ask this question more generally, and that's what I want to do. So I'm going to consider this question for certain kinds of motives. In fact, exactly the motives that come up in Gross-Zagier. So the motives of interest to us. So I'll just say the L functions of interest to us in the stock will be of the following form. Okay, so remember in Gross-Zagier, they proved that when you take the L function of the elliptic curve over K and take its derivative, it's related to the Néron-Tate height of the Tigner point, right? And the way the Tigner point is constructed is you construct a point on E over H and then trace it down. But instead of just taking a simple trace, you could have put in a character of the class group as well. Okay? And Gross and Zagier also prove a formula of the following form, where if you throw in a character chi of the class group, then you get the following. You get a kind of twisted L function. So you take the base change of f to k and then twist by the character chi. Okay, that's the L function. So chi in Gross and Zagier was a character of the Galois group of H over K to C cross. Now, there's no particular reason only to look at finite order characters. You can think of chi, by the way, via class field theory, you can think of this as a character of the ideals of K. But there's no particular reason to restrict to finite order characters. In fact, there's good reason to look at infinite order characters as well. Okay? So what I'm going to do is the L function that I'm going to look at is the following. I'll let f be a new form in, say, sk of gamma naught of n. Because it's gamma naught, k has to be even. I'll let k be an imaginary quadratic field. And I'll just assume for simplicity that k is unramified at n. And now I'll take chi to be a Hecke character of k. And this may be infinite order, so it has, I want it to be algebraic, so I'll just say it has infinity type L0. Okay. So these are the two things that are important, the two sort of invariants I want to look at, the weight k of the form and the infinity type of the Hecke character. All right, and to keep things simple, let's look at, we looked at unramified characters over there, so we also look at unramified characters over here. Let's say it's an unramified Hecke character. OK. And the L function that I'm interested in is exactly this L function. That you take the base change of f to k, you twist by chi. Okay, think of it, and this you can think of it this way, or you can think of it as the Rankin-Selberg of f and the theta function associated with chi. So viewed in this way, this is a degree 2 L function over k, and this is a degree 4 over q. Okay. So that's the L function I'm interested in. Now, the center is going to be L plus k over 2. Okay. And we want the center to be an integer for the Bloch-Beilinson conjecture, so we need to assume that L is congruent to k mod 2. Okay. So assume. All right. Now it turns out that because I assume that f is on gamma naught of n and chi is unramified, when you look at this motive, it's self-dual. So the sign in the functional equation turns out to be either plus or minus 1. Okay? And so you can ask yourself the following question. Suppose the sign is minus 1. Right? Can I produce a variety that contains this motive and a homologically trivial cycle of the right dimension or codimension on this variety that corresponds to the vanishing of this L function? Okay? And that's the question I want to consider. Okay. So I'll need a little table. So I'll erase my beautiful picture and draw this table. Chalk. OK. So I told you that the global sign, which I called epsilon, is plus minus 1. But this global sign is, in fact, in a natural way, a product of local signs. So it's a product of epsilon v over all places v. So here's the table. I'm going to split this into two cases where k is bigger than L and k is less than equals L. And here, I'm going to split this into two cases where epsilon is plus 1. So this is the global sign. Epsilon is minus 1. Okay. Now, the reason I broke it up that way is because whether k is bigger than L or less than equals L tells you what epsilon infinity is. Epsilon infinity is determined completely by the Hodge structure. And so in this case, it turns out that epsilon infinity is minus 1, while in this case, it turns out that epsilon infinity is plus 1. Okay, that's very important. Okay. So now if you think back to Gross and Zagier, right? Gross and Zagier are exactly here in this picture, in this part of the diagram, where epsilon is -1. Okay? But more than that, they had very specific restrictions on k and L. So in Gross-Zagier, we had k was 2, L is 0, right? And you had this assumption that k was split at all the primes dividing n. Okay? And that tells you that all the local signs epsilon v are +1 for all finite v. Okay? The sign at infinity is -1. All the local signs at finite places are +1, so the global sign is -1. Okay? And that's the setting that Gross and Zagier studied. Okay. Now, I'm going to sort of relax these assumptions bit by bit. But before I do that, I want to tell you what more you can say just in the Gross-Zagier case. Right? So going back to the Gross-Zagier case, what they showed was that if you take the Néron-Tate height of this point, this is the derivative of the L function at the point 1. Right? But it turns out there's not one such formula, but there are 3 such formulae. Okay? That one should. So this is the first one. The second is due to Perron-Riou. So this is Gross and Zagier was proved about, I think, 85, 86, about that time. Right? It appeared in 86 at least. And then soon after, Perron-Riou, imitating Gross-Zagier, proved a p-adic analog of this formula. So there's a p-adic analog of the Néron-Tate height. I'll just put a p out there. And what she showed is that this equals the derivative of some p-adic L function. So I'm going to call that p-adic L function LP1. And the way we're going to write this is LP1 of f chi evaluated at the trivial character. I'll explain what this means in a second. And this appeared soon after, I think, around in 87 or so. And then more recently, in a paper with Bertolini and Darmot, so this is, I think, I'll call this BDP. This appeared in Duke in 2012. What we showed was we studied a different invariant of this point. We looked at the p-adic logarithm of this point. And so there's a third formula which says that the p-adic log squared of this point equals not the derivative of p-adic L function, but the value of some other p-adic L function. So I'll write this. I'll call this other p-adic L function LP2. So it's LP2 of f chi evaluated at the trivial character. Okay? So let me say a word about the difference between these two formulae and the difference between these two p-adic L functions. So why is it that we have 2 different p-adic L functions? Okay, so one thing I should say is here, Perron-Riou assumed that f is ordinary at p, while we assumed here that p is split in k. So this itself should tell you that there's some sort of dichotomy going on. So the 2 p-adic L functions correspond to the following picture. Okay, so the point is that you have k, which is a quadratic extension. I'll write k infinity for the ZP2 extension of k. And inside here, you have on the one hand the anticyclotomic extension and the cyclotomic extension. And very roughly, these 2 p-adic L functions, LP1 and LP2, these are constructed by interpolating the L values L fk eta s for various critical values of s, where eta is, or maybe I should put L fk chi eta, because I want my chi in there, where eta is a character of k cross. So eta is a Hecke character of k that, viewed as a Galois character, factors through the Galois group of k infinity. That fact, I'll just say factors factoring through the Galois group of k infinity over k. Okay. But the point is that when you look at these L values, and you look at the transcendental part of the L value, the period that you get depends very much on whether the weight of the form is bigger than the weight of the character or the other way around. Okay? And so the reason you get these two different p-adic L functions is in one case the period is the Peterson inner product of f. In the other case, the period is a CM period associated with the field K. Okay? So that sort of explains why you have two different p-adic L functions. And very roughly, you can think of these p-adic L functions as living in ZP bracket G, where G is the Galois group. So G is, which is non-canonical, which is a power series ring in two variables. And what happens is that one of these p-adic L functions, namely LP1, vanishes at S0, at all points of the form S0. And so what you do is take the derivative in the t direction. And this is what comes up in Penrose. But the other p-adic L function does not vanish even at 0, 0. In fact, 0, 0 is not in the range of interpolation. So it just says LP2 at 0, 0 is what comes up in BDP. Okay? So I just want to emphasize that there's this sort of dichotomy. And you get these two different p-adic L functions. And they give you two different formulas in the p-adic world, while in sort of usual world, you only have one formula. OK. So even in this one case, there are three formulas. And now you can start sort of relaxing these assumptions and seeing where you go. So the first thing we can try is let's take k equals 2r and L equals 0. Right. So right here. All right, remember we're in the -1 case, right? We're here where the global sign is -1. So we really want to find a variety whose cohomology contains this motive, and we want to find a cycle. Okay? Now, f has weight k, which is 2r. And so in this case, I believe the cycles were constructed by Deligne, but I'm not sure. These cycles are called Tigner cycles. And so how do you construct them? Well, you have to realize this form in the cohomology of some variety. And you can do this using a Kuga-Sato variety of the right dimension. So in this case, f occurs in the cohomology of the Kuga-Sato variety wk minus 2. So the way I want to think about this is wk minus 2 is say fibered over x1 of n. So you take the universal elliptic curve over y1 of n, then take the k minus 2th fiber product of this over y1 of n, and then you have to compactify this appropriately at infinity. And so the construction of this variety is due to Deligne, but the point is that f occurs in the middle dimensional cohomology. Sato and OK. OK. Right. But then there's the question is, how do you find the cycle in here, right? OK. And so it turns out what you do is you still look at a Tigner point below here. And now if you think of what the fiber above a Tigner point looks like, it's going to look like some number of copies of a CM elliptic curve. K minus 2 copies of a CM elliptic curve. And k is even. So you can write this as a cross a to the k minus 2 over 2. Okay. And now the intuition is that somehow what you want to do is when you think of this as a fibration, you want to pick a sort of an extra cycle that doesn't deform in the family. And there is an extra cycle here. It just comes from the graph of square root of minus d. So the graph of square root of minus d, where d is the discriminant of k, minus d is the discriminant of k, gives you a sort of extra cycle over there. And now you have to take the k minus 2 power of this, and this has to be modified in some way by applying certain projectors. And that's what gives rise to the cycle. And then it turns out that Zhang and Nekowar, so Shouwu, studied exactly these cycles, and they proved the analogs of these two formulae, the first two in that case. Okay, so that's fine. So we're still at k equals 2r and l equals 0, but now you might relax this more. You might say, well, let's just take k bigger than l. Okay, let's relax this and see what happens. Okay, so now the cycles were constructed in the BDP paper, and we call these generalized Tigner cycles. And the point is that now you have not just your form f, but you also have this Hecke character which has type L0. So the variety we look at is the wk minus 2, and then you throw in L copies of the CM elliptic curve. Pick one of these curves and you throw in L copies of that. This is still fiber over x1 of n. And just for, let me call this A prime, just to distinguish it from general A. OK, but now if you look at the fiber over a Tigner point, it's going to look like A to the k minus 2 cross A prime to the L, where A prime and A are isogynous elliptic curves. So you can pick some isogeny from A prime to A. It doesn't matter. And remember that because k is bigger than L, and k and L are congruent mod 2, k is at least k minus 2 is bigger than equals L. Okay? That's important, right? It's elementary numerology, but it's everything works out because of this. Okay. So there are sort of more factors here than there are over there. Okay? Which means that I can write this as A cross A prime to the L. And then I have some part that's left over, which is A cross A. And it's going to be to the k minus L minus 2 over 2. And again, you want to produce an extra cycle that doesn't deform. So on this factor, you should take the graph of square root of minus d. So in this factor, you can take any isogeny that you want, and it's not going to deform in the family. Okay, so now we get these cycles. And in fact, what we proved in that paper was this third formula in that setting. Okay. The first formula was just proved in the PhD thesis of my student, Arish Nidman, who's defending on Monday. So very appropriate question. All right. Oh, no, actually, sorry. He proved the second one. OK, and he proved lots of things towards the first one. But there's something that's not matching us yet, which he needs to fix. Yeah. So it's almost there, but what is it? By Monday, hopefully. Yes. Well, he only has to turn it in by later in May, so there's time for him to work on this stuff. OK, I hope he's watching the video. OK, so right. So all of this was in this case when k is bigger than L, but epsilon v is still plus 1 for all finite v. OK, so you'd like to relax that, and that's not so hard to relax. Sorry, not easy, not difficult to relax. So let me make a definition first. Okay, this is the key definition. So I'm going to define a quaternion algebra B. So B will be a quaternion algebra over Q. And I'm going to define it by just telling you what all the finite places where it's ramified are. Okay? So it's going to have the property that set of finite V such that B is ramified at V is exactly equal to the set of finite V such that epsilon V is minus 1. I have the local signs epsilon v, right? So I make a quaternion algebra by telling you what finite place is ramified. I'm going to pick exactly those where the local sign is -1. And of course, the ramification at infinity is determined by whether you had an odd or even number of places where finite places where epsilon v is -1. So in each of these situations, you can define a quaternion algebra. And if you figure out what's happening with the signs at infinity, in this case, b is indefinite. In this case, b is definite. In this case, b is indefinite. And in this case, b is definite. OK? That's the numerology. So so here, everything I described so far was on x0 of n or x1 of n. But in general, you have an indefinite quaternion algebra. You can make a Shimura curve associated with indefinite quaternion algebra. And everything goes through. Okay? So everything goes through using Shimura curves. OK? So that's great. All right. So I want to talk about these two cases first. In these two cases, the sign is +1. So you don't expect, not looking for a cycle on a variety. But you'd still maybe like a formula for the L value now, which is not typically going to vanish.
Which of the three? All three?
No. I'm just going to talk of these two cases now.
No, in bottom left.
Bottom left? Yes. Oh, everything should. Yeah, OK. In the sense that you can make the cycles. I'm not saying that people have written out the entire proof in all these.
Three different versions you gave.
Yes. Yes. So.
Can you talk about which version or all three?
OK, so let me just say this, that the third thing has been done. Right? So in this particular case, it was done by my student Hunter Brooks. And then over totally real fields, this has been done by Liu Zhang as well. OK? So this one is done. And these two, I'm not sure that somebody has written this out. But I'm saying there's no difficulty in at least constructing the cycles. But then it's a matter of computing. So, all right. OK, so what does one expect in these two cases? The global sign is +1. You're not looking for a cycle, but maybe you'd still like the L value, right? You'd like some expression for the L value. Maybe as the square of something to reflect the fact that you get squares at the center typically. And in fact, this is exactly, both these cases are covered by a single formula. This is a formula of Walsh-Perchet. Okay? Walsh-Perchet proves a formula that relates toric periods to central values of L functions. And this is exactly Walsh-Perchet. So this is a single formula that covers both these cases.
That doesn't require anything about the algebra, like the Eke character.
Sure. Yeah, but it requires this. It requires something about this. Yeah. There is arithmetic, but there is arithmetic when the character is algebraic. Yeah. All right. Fine. OK. So right. So there's Walsh-Perchet's formula in both these cases that says that the central value is the square of a period. Okay. All right. So that takes care of all these three cases. But the question I want to talk about is this case. Okay. The problem in this case is that the sign is -1. So you want to find a cycle on some variety. But the only information you seem to have is this definite quaternion algebra. And what do you do with the definite quaternion algebra? If you look at the associated Shimura variety, that's a finite set of points. And you don't really have anything to go with. Okay? So in the last 10 minutes, I'm going to explain to you what we think we can do with this. So I'm going to give a construction, but it'll seem horribly unmotivated unless I say a few words beforehand. So I'm going to.
What about these old papers of Gross?
No, that's that case. Gross
He didn't give any.
is this one.
Yeah, okay. There's the period formula, and then there's interpreting things in terms of height.
Yeah, but that's just interpreting it. It's not nothing new. Gross was after Walsh-Perchet, in fact.
Yeah.
And it's a special case of Walsh-Perchet. Yeah. So, all right. So I want to do the case k less than equals L. So let's look at the very simplest case, k equals 2, L equals 2. Okay. So we're looking at L of f cross theta chi s, where f has weight 2 and chi has type 2, 0. Now, one way you might try to study this is by writing chi as the product of two characters, chi1 and chi2. both of type 1, 0. Okay. If you did this, then you could consider the triple product L function, where you take L of f cross theta chi1 cross theta chi2. And this has the property, because chi1 and chi2 come from the same imaginary quadratic field, that this factors as LF k chi1 chi2 s times L of fk chi1 chi2 rho s, where rho is the complex conjugation of the. Now chi1, this is the character chi you're interested in, and this is some other character eta. And remember, the sign here is -1. And you could have picked things such that maybe the sign there is plus and the sign here is minus. Okay. Now here you have 3 weight 2 forms. If the sign is minus, then you're in the range where the triple product cycle appears. This is the modified diagonal on the triple product. Okay. So here you could construct so-called modified diagonal. And that would give you a cycle. The only problem is that when you sort of compute invariance of the cycle, you're not going to pick up just this L function, but also this additional spurious L function, where you have this twist pi, where you have LFK eta s. And for aesthetic reasons and for other non-aesthetic reasons, you'd like that L factor not to be there. Now, remember that this guy gave us somehow this definite quaternion algebra B. If you want to construct the modified diagonal, the theory of the triple product, where you have to look at epsilon factors, tells you that there is a particular inner form of GL2 that you have to move to. And that particular inner form will come from, so that will give you some other quaternion algebra B1, which is going to be indefinite. Okay, so the picture is this is indefinite. This is definite. And this guy, you're at the center, and the sign is +1. So Walsh-Perchet applies. And Walsh-Perchet will tell you that there's yet another inner form. So this corresponds to some B2, which is going to be definite. OK? And of course, B, B1, and B2 are sort of determined by local signs. So there's going to be some relation between them. And the relation between them is exactly that B1 equals B times B2 in the Brauer group. Okay, so the product of any two of them is a third in the Brauer group. So the situation is that I have K sitting inside B. K sits inside all of these fields, all of these quaternion algebras, and B is equal to B1 times B2 in the Brauer group of Q. All right. So now I want to say that now I'm going to describe the construction. This is joint work with Ichino. It's ongoing joint work with Ichino. And the point is that somehow we want to use these other quaternion algebras, but not use that other character eta. Okay. So here's what we do. Remember that K sits inside B1 and B2. So you can think of B1 and B2 as right K spaces. And there's a natural way to think of them as Hermitian K spaces. So they're two-dimensional K vector spaces with a natural Hermitian form. All right. Now we take the tensor product of B1 and B2. And so this inherits a natural Hermitian form, right? Just the tensor product of the two Hermitian forms. And this is 4-dimensional as a K space. So now what we do is we take this Hermitian form and multiply it by a trace zero element to make it skew Hermitian. So make the skew Hermitian. Okay. So there's a skew Hermitian form, which I'll write as that. Now remember that this is a right K space, but now I have to use the quaternion algebra B. Okay. So it turns out that there's a natural way to make V into a right B space, extending the action of K. So V is going to be, V was 4-dimensional as a K vector space. It's going to be 2-dimensional as a right B space. But moreover, there's a natural way to construct a form a B form, which I'll write with the double brackets, on V in such a way that you can recover this Q-Hermitian K form by taking a projection. So B is going to be K plus the orthogonal complement to K. So you can project onto the first factor, and the relation between the forms is going to be that when you project the B-valued form, you recover the K-valued form. OK? All right, so what does this buy you? Sorry, say it again. Which?
You now have triple products.
Oh no, I don't have triple products. I don't want to use the triple product. That's the whole point. I want to just do this L value without using the triple product. I'm still doing that one. Okay? I want to motivate this B1 and B2. Okay? So the triple product motivates the introduction of these quaternion algebras. But I don't want to use the character eta. I want to do it without that. OK. So the point is you have V, which you can think of as either a K space or a B space. And there are these two forms which are related in this way. And now you can take the unitary group, or GU KV. And because the two forms are related in this way, the unitary group GU BV, in fact, is contained inside GU KV. Okay. But now B1 cross and B2 cross both act on the left on V. And using that, it's not hard to see that if you take the connected component of this, this is just B1 cross cross B2 cross mod Q cross. Okay. On the other hand, this group you can check as just GU22. All right. Now, B1 was indefinite, and B2 was definite, right? So if you take the Shimura variety associated with this group, this is in fact a Shimura curve, or a bunch of Shimura curves. So I'll call the Shimura variety Y, and I'll call this Shimura variety X, and you get a map from Y to X. And because what you have is what you have are Shimura curves over here, in fact, the form F, and the form F transfers to B1 and B2, it contributes to H1 of the Shimura variety Y. Okay? So F contributes to H1 of Y. On the other hand, one can show that if you take the character chi, which is type 2,0, and take the theta lift of chi, so this is the theta lift from GU1 to GU22, then this contributes to the cohomology of the Shimura variety associated with GU22, and in fact in several different degrees. Contributes to H2, H4, and H6 of X. So it's a non-tempered representation. All right. So the point is somehow we've flipped things around. The variety, the larger dimensional variety is now going to be the one associated to chi rather than the one associated to F. Okay. So let's take, so the ambient variety now is going to be X cross Y. And if you take X cross Y, then the theta function lives in, say, H2, H4, and H6 of X. And F contributes to H1 of Y. So the motive that you're interested in, MF chi, lives in three different homology spaces. It contributes to H3, H5, and H7 of this variety X prime. And because the L function vanishes, you expect cycles in three different codimensions. Okay? So this guy will contribute. You should get something in CH20. This will give you something in CH30, and this should give you something in CH40. Now, the only obvious cycle you can write down comes from the diagonal. So there's a diagonal cycle because Y embeds in X. Okay? And so you have a diagonal cycle, and that's an element here in CH40. And so now we go back to what the Bloch-Beilinson conjecture tells you. Right? So this motive occurs in these different degrees. If you had a cycle here and a cycle here, then the intersection should be related, the arithmetic intersection should be related to the derivative. If you found something here, its self-intersection should be related, right, to the derivative of the L function. But unfortunately, this is something that happens often with the Hodge conjecture or with the Bloch-Beilinson conjectures. When you expect things to happen in several different dimensions, if you can construct the largest dimensional one, you can intersect with a hyperplane section and go down. But you can never go in the opposite direction. All right. So all we have is this one cycle here, delta. And so you might ask, what can we do with this? Okay. All right. And now this is where you go back to this blackboard and note that it's only the first two formulas that require two different cycles because you have to intersect them. The third one only requires one. Okay. So what we hope to prove is the analog of the third formula, so where you can compute the p-adic logarithm of the cycle. And we expect that to be related to also a p-adic L function, but it's going to be flipped around. In these cases, we fixed f and we varied chi to construct the p-adic L function. The p-adic L function that will show up over here, you fix chi and you vary f in a Hida family. So you start off where the weights originally are 2, 2. So f has weight 2, right, and chi is type 2, 0. You keep your chi fixed, but you put f in a Hida family where the weights become larger than 4. So look at g, where the weight of g is larger than 4. And now when you look at the Rankin-Selberg, this is sign flip again, because you flip what happens at infinity. So you get a p-adic L function, and that p-adic L function is non-vanishing. And you can now evaluate that at your original form f. And so what we expect is an analog of this BDP formula, where the logarithm of the cycle is related to this other p-adic L function. Okay, so this is very much work in progress, but just leave it at that.